Welcome everyone to the Open ZFS Developer Summit for 2024. I almost said 2014. So today I want to talk about how we can scale ZFS for the future and basically be ready for the hardware that's coming in the future. Mostly about flash, but even also, the silly large hard drives that are also coming. So to walk through that, we'll start with a quick introduction to me and talk about some of the problems ZFS currently has with scaling, and then dig in on some specific issues, being what do we do about these flash devices that are coming with massive sector sizes, and how can we make ZFS work with that? Some of the problems we have around queuing, making sure that we can actually keep these ultra low latency devices busy with work, and then how can we deal with huge disks, especially when we're looking at things like a core vault that might expose a 700 terabyte LUN as if it was one disk, and then want to present a dozen more of those. And then we'll talk about this kind of summary and takeaway, and then I'll take some questions. So in case you don't know me, I'm Allan Jude. I'm the co-founder and principal solution architect at Clara, which is a professional services company around ZFS and FreeBSD. And so if you need support for ZFS or want to get a feature designed, then definitely come talk to me. So getting straight into things, ZFS has some scaling problems. Some of that has to do with the fact that it was designed quite a while ago at this point. We've been having this conference for 12 years now, and before that, ZFS has already been around for quite a while. And so when ZFS was designed, the future looked different than what it does today. We never correctly guess what the future is going to be. But hard drives got bigger faster than we thought, but IOPS didn't go up. But flash also took off maybe more than we expected. But even to put that all in context, the first SATA hard drive, as in transitioning away from IDE to SATA, didn't ship until the year after they started building ZFS. So, a lot has changed since when ZFS was being designed. And at the time, 1 terabyte was a lot of data, and a 10,000 RPM hard drive was fast. And flash was new. You were never going to have that much of it, and it was going to wear out if you used it too hard. And a lot of that has changed. But ZFS did a lot of work that very helpfully optimized for hard drives. Knowing that, hey, we have lots of CPU time, and the hard drive's always going to take somewhere in the measure of milliseconds to do anything. So we want to use the CPU and decide how we're going to lay it out and how we're going to request it, and can we aggregate this more to get the most out of the hard drive. And that has served us very well. But as we get to devices that are going to take single-digit microseconds to respond to things, we maybe don't have the same luxury to decide to aggregate a bunch of stuff and go to sleep and then wait for the result, when the result's probably going to come back faster than the smallest amount of time we can sleep for. And so some of the things that we thought would be true forever that really aren't. The first being that, sectors on hard drives are always going to be 512 bytes. We learned the hard way that that wasn't true when 4K native came out, but as we're going to talk about later, it's going to get crazier than that. And some of the initial design decisions in ZFS might come back to bite us, and what can we do about that? And we also assumed that the CPU was always going to be faster than storage, that we would be able to take some time to massage the IOs before we send them to the disk, and that was never going to be anything but in the noise. But now the storage can often have lower latency than anything else, and we have to be able to deal with that. And we also assumed that avoiding seeking was actually going to provide some benefit. But now, everything that's not spinning rest, the seek is not even a thing. And so spending a lot of time trying to optimize for that, or even optimization of we assume the outer tracks on the hard drive are faster than the inner ones, so we should bias towards those. That's totally not the case with flash. Yeah, and because the latencies can be so low, sometimes we actually be better off not trying to do any massaging on the I/O before we send it to the device, and we just have to send it as fast as we can. So the big thing that I want to talk about today is what we're going to do about large sector devices. In your typical flash device, there's a flash translation layer that takes the concept of a logical block address that a hard drive had and maps it to where it is on the flash, so that as that flash wears out, we can move that data to somewhere else while it's still addressed by that same LBA. The problem is the flash translation layer has a granularity of the sector size. And so as devices have gotten bigger and bigger, we usually have up to 8 or 16 terabyte NVMe volumes now. The number of even 4K sectors on a 16 terabyte NVMe is a lot. And NVMe has to generally try to keep that table in memory in order to be fast. But that's requiring more and more RAM on each of these NVMe devices, and that makes them more and more expensive. As vendors look at building 150 terabyte NVMe volumes, or devices, they need to be able to save some money by not having as much DRAM on the device, and so they would like to go to a larger sector size so that their flash translation layer will be smaller and will fit in less RAM. So that means much bigger sector sizes. We've seen vendors talking about 32 or 64 kilobyte sector sizes. And in ZFS, we can support a 32 kilobyte sector size, but it comes with a lot of trade-offs that most people I don't think are going to want to make. And most of these devices will do a read, modify, write, and be compatible with a smaller sector size, but that's going to have a performance cost and a wear leveling cost that we probably don't want to have to make. So, what are we going to do with that? The biggest problem is obviously the Uber block ring. We have 128 kilobytes reserved for the Uber block, and if our sectors are 32K, then we're only going to fit 4 Uber blocks, which doesn't give you much of a window to rewind if something goes wrong. And so what can we do about it? So briefly walking over what the label at the start of a drive looks like today. We reserved the first 4 megabytes of a device. The first 8K is mostly padding. It's there because a lot of previous file systems assumed that first couple of sectors is where we might put the third stage bootloader or something, and they might try to clobber it, so we just left it blank to make sure nobody else would use it. That was originally 16K, but we carved off the second half of it to put the boot environment data. That was a collaboration between FreeBSD and Delphix to build a system where you can flag which data set to boot from next time and make it one time only, or to do the failed boot counter and a bunch of other stuff. So there's a little packed NV list in there that tells us extra instructions to use during boot. Then we have the vdev config, which is basically the remaining 112 kilobytes there, and that again is an NV list, and it tells us about the configuration, a little bit about the pool, and about this specific top-level vdev and its children. So if you have a couple of RAID Z2 vdevs in your pool, on each disk it will know about the RAID Z2 it's in and its kind of siblings, and that's it. And then the end of the first label is this 128K ring, where we put our Uber blocks that are generally 1 kilobyte apiece. But we round that up to whole sectors to avoid problems with shorn writes or just not being able to atomically update them. So that meant when we had 5 12-byte sector disks, if we take that 128K and divide it by the 1K of an Uber block, we had 128 Uber blocks, and that gave us quite a bit of ability to rewind or go back if something went wrong. But as we upgraded to 4 kilobyte sectors, it turns out we only get 32 Uber blocks now, which has mostly been enough, although we've definitely seen cases in the field where it would have been really handy if we had just a couple more. We ran into one case where some bad things happened and the Uber blocks got clobbered, and out of a couple hundred Uber blocks available across all the labels on all the vdevs, there was one that was still the good one. And it made things quite challenging. It would have been nice to have a bigger ring there. And then we've started to steal slots out of that. The MMP feature for the multi-mount protection uses one of those Uber block slots for its sentinel of this pool still alive. So that means we only actually have 31 Uber blocks. And then if you store a checkpoint, that freezes an Uber block as well, and means you can really get even fewer Uber blocks. And then we have the second label, which is basically identical to the first. And then there's also a third and a fourth label at the end of the disk. And then the slack area is the rest of that first 4 megabytes, just to align the start of the raw data with this 4 megabytes. And that area is used on some operating systems for the bootloader, and is also used by RAID-Z expansion as kind of some scratch space to bootstrap itself from, because it needs to temporarily rewrite the first couple of DVAs at the beginning of the VDEV. And so at the end, there's no slack area. It's just these 2 512 kilobyte labels. So after discussing it with Don and a few other people, what we're proposing to do is to take maybe the whole first gigabyte of a VDEV. Probably we'd only use this layout on disks that are at least a terabyte, rather than every disk. We still want to support the case of small VDEVs for testing, and people are deploying VMs where they pay for every megabyte of space. They might not want to waste a bunch of it on Slack. But as we now, hard drives generally are 20 terabytes and up now, and even NVMe are usually definitely over a terabyte at this point. That's kind of in the noise to just take this extra 1 gigabyte instead. So basically, each label would go from 256K to 256 megabytes. And partly to avoid compatibility problems and so on, we'd probably keep padding at the beginning for that whole first 16 megabytes. Part of what I assumed here is just a worst possible case that the sector size could go up as big as 16 megabytes. And so we want to make sure all the offsets in here are multiples of 16 megabytes. And so we keep the boot environment area. Maybe it doesn't need to be that big, but if that's going to be our smallest quantum, then everything has to be at least that big. And while we keep the name value pair thing we have now for each VDEV to know about its siblings, it might actually be useful, as long as we don't update it too frequently, to have the whole pool config on every disk. Especially when things get hairy, it'd be nice to have a known good copy of the pool config that didn't require reading from the MOS, which requires actually having assembled the whole pool again. This also means that when you go to import a pool where there's some missing devices, it can at least tell you which devices are missing, instead of saying, well, I know about these ones, and I know from the pool-wide config at the top that there should be n VDEVs, and I only see half that many, but it isn't able to tell you anything about what's missing. And so since we have all this room now, maybe we can take the luxury of storing the entire pool config in there. And then using the last half for the Uber block ring, having 128 megs instead of 128 kilobytes means that we can have as many as 32,000 Uber blocks with 4K, or at least 1,000 if we get all the way up to 128K sectors. And now we have a lot more ability to go back and look at what the pool looked like before and make sure that we can import stuff. And with a little bit of space left between those, maybe we have a completely separate area reserved for the special Uber blocks, like the multi-mount protection and the checkpoints for rewind and so on. But the other thing we might look at here is purposely setting aside in some kind of like round-robin database fashion really old Uber blocks. Obviously, if we have 32,000, we probably don't need any more than that. But if we're down to a smaller number, it might be handy to just be able to go back 5,000 transaction groups and say, what did the Uber block look like then? Whereas right now, when you only get 32, even just knowing 256 transactions ago would be really nice, but we don't have that. And maybe we'll find a use for it later. We don't want to have to perform this exercise multiple times. So if we're going to go all the way to gigabyte, we'll leave the whole last bit as scratch base. And maybe that'll also speed up RAID-Z expansion, but we might want to define how much of that can be used for scratch space and how much is actually reserved for some future use we might actually have. And maybe we decide against some of these segments and keep more reserved space in each label in case we need it. But would like to have more conversations about that later today on what we can do around this. So some of the considerations for this, obviously, we want to minimize the time we're massively changing the on-disk format. So would like this to be a longer conversation and kind of figure out all the things we might need in the next 5 or 10 years and make sure we've reserved space for them, and for the things we don't know we need yet, as we've kind of looked at the lessons of the last 20 years. But the other big question is, how are we going to identify the new format? Do we just put some marker in that little reserve space at the beginning that says, where older ZFS is going to look to find the old label? We have some dummy label that says, oh, this is a V5001 label or something, so the older ZFS will be like, I see that ZFS, but I'm not new enough to understand it, or something like that. Some easy way for it to define that. And obviously, make sure that if you try to import it, it doesn't say there's no pool here. It says, you need to upgrade your ZFS to be able to import that. But what are the trade-offs between bumping the version number again or just having that be a feature flag? The big thing is, if it's not going to be able to read the label, packing the whole feature flag list and so on into a dummy label is a lot more work than just incrementing the version number. But again, that's a conversation we can have. And then, like I said, about maybe we decide where the cutoff is for switching to this new format. Obviously, if people have 100 gig disks, they might not want to give up a whole 1% of it for the labels. But at the same time, maybe they do for some reason or because they know they're going to grow the disk in the future, especially in the cloud where the size of your disk is not as fixed as it is with real hardware. So I guess on to the next subject, which is queuing, which is everybody's favorite British sport. So there's a couple things that we need to look at with ZFS to kind of be ready for the future. The first one is when we actually issue I/O. With the way the VDEV queue works right now, the main time we decide to send more I/O down to the VDEV is A, when somebody queues even more I/O, or B, when some I/O completes. And the kind of context switching back and forth here can mean we end up spending a lot of time with nothing in the device queue because it completed faster than we would have really expected because it was designed for hard drives. So quote directly from the source code, every time an I/O is queued or an operation completes, the I/O scheduler looks for the next operation to issue. And maybe, part of that is just maybe we don't want to be issuing one operation at a time, especially if a device has 64 queues that have a depth of 64 each. Maybe one at a time isn't how we want to really consider issuing I/Os anymore. And also, maybe we want to lighten the amount of work done by the completion handler. When an I/O is done and we get a notification about it, now is maybe not the right time to be thinking about what other I/O should we send to the device, but instead just let's get this data back to the user as quickly as possible. The other problem is we do this one class at a time. So the VDEV queue is broken up into synchronous writes, asynchronous writes, synchronous reads, asynchronous reads, and scrubs. And we kind of issue from each of those classes one at a time. And knowing that we have 64 queues, maybe for NVMe devices, we should be issuing from all of the queues all of the time. It's not likely that the device is actually going to get saturated and not be able to handle the amount of I/O we're sending it. In most cases, we're not seeing NVMe devices getting to 100% busy very often at all. And so we might have to try harder or use more threads to be pushing I/O down to the device. And maybe what we should have is dedicated threads that are just for issuing I/O so that they're never context switching away. Another thing we might consider is it time for direct dispatch? Instead of after we issue the I/O, we go to sleep and some other thread gets woken up to tell us that it completed, especially the way NVMe works, each queue is tied to a CPU core. Maybe it makes sense that knowing it's only going to take 5 or 10 or 15 microseconds, that we issue the I/O and just wait for it to be done and then deal with it in line, instead of having as much queuing. But then we have to kind of auto-detect what's in NVMe and what isn't, and kind of have these different modes for the queue. And that gets complicated, but it may be what we have to do in order to push ZFS to being able to get the number of IOPS that these devices can. And then a conversation we had a bit yesterday about the kind of burstiness of I/O with especially asynchronous writes. Today, when you do a bunch of asynchronous writes, they accumulate in the dirty buffer in the arc, and then when we go to flush that transaction group, we write out all that data in a big burst. You know, we've all watched Z equal IOstat, and you see 0 megabytes written for 1 second, 2, 3, 4 seconds, and the 5th second comes and you just slam down 2 gigabytes of data. And then you go back to sleep. Nothing written for 4 seconds, and then on the 5th second, another 2 gigabytes being written. That works very well for hard drives where you don't want the head moving around a lot, and you'll get better read performance by not reading and writing at the same time. With NVMe, that's just not true. And then also, when we start looking at the cloud, often the device you're talking to is virtual and often has rate limits or I/O limits that are kind of artificial. Right? It's just this device does exactly this many IOPS, and you can never have more no matter what you do. If you're slamming down all the writes all at once every 5 seconds, you'll see your read latency is fine, and then there's a big spike. It's fine and a big spike. When you're writing, you're using up all your IOPS, and then your read latency goes out to lunch. And so can we start writing some of that data sooner and kind of smooth out that 5-second burst? We can tune it so that we just flush every 1 second, but even then, that's still very bursty as opposed to just kind of writing data as it's ready, and then when we hit the transaction sync, we just finish out the indirect blocks and whatever's left.
As you know, with the drives getting bigger and bigger and bigger, and et cetera, how is ZFS handling the space reclamation issues, i.e. on SSDs, because that's to write a certain amount of blocks, they have to rewrite it again with zeros before you can rewrite it again. So is there anything ZFS is doing to kind of speed that up?
So right now, ZFS doesn't do anything special to deal with the fact that if you write too much too quickly, it can trigger the SSD to go into garbage collection in order to find space. That's usually a bit less of an issue because ZFS is, depending on how you configure it, been diligent about trimming the space so that the disk doesn't have to shuffle things around to find unallocated blocks. It already knows what blocks are unallocated. But it can still happen, and I know, Netflix has done a bunch of work in the I/O scheduler in FreeBSD's disk layer to moderate the rate of writes when it starts impacting the read latency. And it might be something that ZFS will need to look at as we start smoothing out our writes at some point if, as we increase the level of writes, maybe as the write throttle kicks in when we have more and more dirty data, if we see it impacting the read latency, maybe we do want to try to back off and push back on the application saying, stop throwing so much data at me, you're causing latency on the reads. Not something I've considered yet because until we kind of smooth out our writes, we won't be able to see that happening as much. But it may be that the fact that we're doing this in big bursts is already making that worse because we throw the hard drive or the disk a big chunk of data and it has to go find space for it, and it might actually be making that garbage collection worse, whereas if we fed it smaller pieces, it would kind of do that in smaller chunks as it went.
Yeah, that sounds good. I was only thinking about that. You would be familiar with that. Yeah. I said Steve would be familiar with this. I was thinking about this largely in the video space because they do a lot of large writes and there's a lot of sensitivity towards latency and whatever. So that was kind of where that question came from.
Yeah. Cool, thank you. And then the fourth thing, obviously, is queue lock contention. Because the way the VDAV queue works is we queue the work when it comes in, and then we move it as we issue it, but we're basically keeping it on the queue. And so when we get a bunch of completions all at once, which traditionally didn't happen when you had a spinning hard drive with one queue, you got your completions one at a time. But with NVMe, you might get 64 completions at once, and all those completion handlers are now waiting to acquire the lock to take that one ZIO off the queue and mark it as done and call it done handler and so on. And so we can end up contending on the queue lock a lot just because our completions may become in bursts or are coming in faster than we can process them because of the amount of stuff we're doing in the completion handler. And so maybe can we use the kind of private pointer space that the bio layer of both operating systems provides to kind of attach the ZIO to the bio that goes down to the disk. So when we get the completion, we have a pointer to the ZIO that was completed and maybe not have to keep it on the VDAV queue so that we can still find it and call it stun handler and so on, but without necessarily having to take a lock in order to do that. But if we do that, how do we keep track of how many are outstanding and especially find the one that we issued and somehow never got back? Although ZFS doesn't do anything about that now other than wait forever. So maybe it's less of a big deal. So the next item was, what do we do about huge disks? So whether that's the 150 terabyte NVMEs that we're going to build, a big array out of, or as I mentioned, things like Seagate's Core Vault, which is basically a giant chassis doing something like D-RAID in hardware. And so when you create a pool, you're getting a bunch of 700 or 750 terabyte LUNs to make a 10 petabyte pool out of. And the way we size things in ZFS is maybe not ready for that. A few terabytes isn't a lot anymore. So the first thing we have to consider is that every disk is not a disk at this point, right? Oftentimes what we're getting is either virtualized from a hypervisor or a cloud provider, or some LUN from a SAN or from something like a Core Vault that's actually an aggregation of a bunch of disks. And then sometimes it's a piece of flash or flash over the network or whatever else it could be. But between flash and virtualization and the various other abstractions, block storage doesn't necessarily resemble a spinning hard drive that much anymore. And what does that mean for some of our assumptions about it? And especially when it's something that's maybe virtualized or kind of hidden from us by other layers of hardware, how do we decide when to treat it like an NVMe versus when to treat it like a hard drive? If it's something that's kind of in between. And even if it's from a hypervisor, if the hypervisor has some cache, some of our reads and writes might have really low latency and make us think, oh, this is acting like an NVMe. But if we exhaust its cache, then suddenly it's going to be slow and act like a hard drive. So auto-tuning and auto-detecting might be a lot more difficult than we would hope. But there are other things we can do to lessen our reliance on assuming that the storage is going to act like a hard drive. With Delphix doing the S3 back storage thing, how much did that change how you treat a VDEV? The other question is about indirection scaling. If you have a 6 terabyte data set and it's all made up of 4K records, that gets really big. That means you have 1.5 billion blocks in that one file. And you have the full 5 of the 6 or 7 maximum layers of indirection in that file because you have so many billions of records. And how does the ARC hash table deal with that? We have a customer that has a 6 terabyte database that they cache in their 6 terabytes of RAM with 4K records. And the ARC does not handle that as well as we would hope. It gets a little better if you use 16K records and some compression, but we have a pull request open for multi-threading ARC eviction so that the read performance from the NVMEs isn't hampered by the fact that we just can't push enough blocks out of the ARC in order to accommodate the reads that we're trying to get, the speed of the reads we're getting back from the NVMe device. And so at some point, do we gotta consider larger indirect blocks or at some point having adaptive indirect blocks? Maybe above a certain level, we should use a larger indirect block instead of just kind of 128K always or even 32K always. Maybe it should, when we get to the point where a file is billions of records, maybe the indirects need to get bigger. We can't change the existing ones, but maybe we can at least make the higher level ones bigger so that we accommodate the total count more directly. And lastly, huge LUNs, as we've talked about on the leadership call a few times. If you get presented with a 700 terabyte LUN, our current logic for how to split it up into metaslabs is probably not the best. At some point, the metaslab logic changed to bias towards more like 3 terabyte size drives, which mostly made sense. But right now you end up with usually about between 90 and 128,000 metaslabs of the smallest size that will accommodate the whole size of the VDEV. Probably need something a little better than that. How much memory a metaslab takes, relative to how much memory a system has on average, it's shifted over the last 10 years. Maybe we can use a little bit more memory in order to have fewer metaslabs. We've seen some customers get pretty pathological performance when they have tens of thousands of metaslabs versus a smaller number, especially as Don found when using large records, the weighting we use for fragmentation needs some adjustment. And without that, we end up loading metaslabs that are not good candidates to find an allocation from. And when we're shuffling through tens of thousands of metaslabs, we often don't find the suitable space we want before we decide we've spent too long on this, just gang block it anyway. And that's inefficient on space, and also means that every allocation is taking a lot longer because we're shuffling through all these metaslabs, seeing that, oh, this one doesn't actually have 20 megabytes of contiguous space that I need to actually write a 16K record on a RAID Z3. One of the ideas we had there was just right now, we aim for 200 metaslabs and keep increasing the size until we hit 16 gigabytes per metaslab. And then we increase the number of metaslabs until we hit the maximum. And then we just increase the size until we come down to below the maximum. Maybe it makes more sense to alternate between doubling the size and doubling the count until we get some kind of middle ground for what's the right count of metaslabs for this device. But yeah, the weighting, it seems that when we came up with the fragmentation weighting, we didn't, 16 megabyte blocks weren't really a thing yet. I think we only supported, 1 megabyte unless you set a tunable to let you go higher than that. And so a lot of the selection logic assumes, search ahead for the next 16 megabytes of space, but with RAID Z3, to allocate 16 megabyte record, you actually need 20 megabytes of space by the time you include the parity. And so we consider any metaslab that has 16 megabytes of contiguous space to be not fragmented at all, which means it looks like it'll satisfy this 20 megabyte allocation, you load it and then it won't. And so, we need to look at that. And I think in general, across a bunch of different places where we use that 16 megabyte limit, we didn't consider that a 16 megabyte record isn't always only 16 megabytes. It might actually be more. And so there's a bunch of places through the code that we're going to need to look at and decide how to improve that. And what is the right number? Or, is there a new define we need that is, this is the amount of space we need to do just one allocation, if it's the biggest it can be with the worst properties of being, a RAID Z3 gang block or something. So to start wrapping that up a little bit, our key takeaways are we need better support for NVMe, especially knowing that they're only going to get faster. Like even today from Micron, you can get a 3.84 terabyte NVMe that will do 1.6 million 4K random IOPS and will easily do 7 gigabytes a second. And you build a pool out of that and you only get about a third of that performance on the IOPS. If you go to bigger sector sizes, you can, even bigger record sizes. If you use 16K records, you can get pretty close to saturating that, the full 7 gigabytes per second. And the default 128K will have no problem getting all the bandwidth out of that device. But when you go down to 4K, you're only getting about a third the IOPS. And importantly, as you add 2 or 4 or 8 of these NVMe, the performance doesn't go up at 4K. You can't get more IOPS no matter what you do. It looks really strange to, stripe 4 NVMEs and get the same performance as you get from 1. What can we do to solve some of those problems? Obviously, the large sector support. We've already seen in the field a customer with a low endurance NVMe that has a 128K sector size. And they kind of naively installed ZFS on it and set up their ZVols for their virtualization. ZFS at least auto-tuned to a maximum A shift of 32K. But that meant their ZVol with a vol block size of 16K, as they wrote the VM to it, they're like, we've only written half the size of our NVMe, but our NVMe reports it's out of space. Where did all our space go? Because every 16K on the ZVol took a 32K allocation because that was the A-shift size. And so once they half-filled the pool, all the space was gone, and they were very confused. And so on top of the fact that we don't support that large of a sector size, and we have all these problems with the Uber block ring not being big enough when we're going to have a 128K sector NVMe, we also have the problem of, do we need to teach the ZVol to have a different default of never less than your A-shift size? And how do we warn the user about the sector size? And maybe we decide that on some of those 128K devices that support emulating smaller reads and writes, that we don't shift the A-shifts all the way up to 128K, but what's the right trade-off there? And then, like I said, capacity scaling, the individual LUNs or physical devices that we're going to build pools out of are just going to keep getting bigger. Beyond tuning the Metaslabs, what else can we do to make sure that we're going to support that properly and not run into scaling issues as we get, to triple digits of petabytes in a pool? And lastly, how do we continue the long-term maintenance of ZFS in general? As we keep adding more and more things, and as the industry shifts a bit, we're picking up a lot more users, and so the kind of ratio of users to developers is more biased towards the users now than it was in the past. And how do we make sure that we can keep up with the incoming rate of bug reports and issue reports and pull requests and so on, and make sure that we continue to scale our ability to respond to the community and to grow the developer community by turning some of those users into developers, and make sure that ZFS continues to perform well and be the best solution that it is today. And how do we keep our testing infrastructure up with the rate of change? And that'll segue into Don's talk after mine, as we kind of talk about what we can do to keep growing the testing framework and making sure that we're finding as many of these problems before we release them, rather than only once users report them. Okay. Are there any more questions? Patrick, which number?
Recently, we had some look on ZFS detection, import process, or earlier process of actually detection. Do we have actually pools there? Mm-hmm. We had a look on Linux block ID code, and appeared it's completely not matching with what ZFS does. It needs complete rewrite. But as part of rewrite, we hit again question that the current design of the label is not exactly oriented for quick checking whether we have something on pull on disk. Mm-hmm. So the first things, obviously, like on a wish list, I'd like to have is some sort of easy signature. If just in a label, read one sector, see signature. Okay, this is definitely ZFS. You look for sectors, found 0 signatures, definitely not ZFS.
Yeah.
So as part of designing new format, that's one thing I'd like to have. Second part,
I really think that just putting every Uber block has its little
that's Uber
signature,
block,
but something in the label that's just read the sector, and if it just says ZFS, ZFS, ZFS over and over again, we know, okay, that's a label, that's a pool, we should look closer.
Yeah, the problem we actually hit is that some disks imported from earlier ZFS version, such as L2ARCs and Spare, they don't have any Uber blocks.
Yeah.
They don't need Uber blocks. They don't update them. So, and block ID code actually looking for a signature of Uber blocks actually failing because there is no signatures. So we need signature as part of a label.
As just part of the label, so that at these 4 offsets, you will see this thing, and that means it's ZFS, even if it's, like you said, just an auxiliary VDEV.
Second part, second issue we hit is that actually to read and release, you need to read all that 120, 118 or whatever, 112 kilobyte of space, and then try to look, is it released? Does it look like released? And so on. And you don't have any sort of knowledge how big shall it be. Mm-hmm. And in context of you jumping to next like 1
Make it
gigabyte.
huge, 128 megabytes. Then,
Yeah, like I definitely don't want to read gigabyte of space to find out do we have any labels there. So I think your design should be slightly different. I think that we should have small, some anchor block or header or whatever you call it. You should have include signature and maybe first small NV list with pointers to other extensions, whatever may grow later. I'm not sure we even need that separation on multiple separate areas, sub-areas for different reasons.
Right, if we make an NV list that just says this is here, that is there, then we have a lot more flexibility in the future.
Yeah, so just gives this general area and offsets within that NV list to the other chunks. We need to compact, we may start compacting them together to easily read in one operation, pretty small, scalable from small hardware, and also can be easily grown to later hardware.
Yeah, I really like that idea.
We could potentially not even separate all those 4 headers by 256 meg. We could put them in old locations originally, where within some padding or whatever areas, and then play compatibly potentially. We can point as either old locations to the question of compatibility, or if we need more space, then sure, move them out, and that pool will only be importable by the new ZFS, obviously. Something that knows about that header block. So that was my second comment, that we need some sort of header to avoid reading
more than we need to, and it gives us a lot more flexibility to change how we're using that label in the future. I really like that.
Is that something we can do ahead of time?
Well, basically, as part of the redesign, we would,
I mean, right now, I'm deploying X amount of petabytes. I don't want to have to go and redo that in 6, 8, 12 months.
Right, so
Can I resize that initial one during deployment now and prep for that?
Currently, there's no way, to repeat the question from Stu, is there something we can do for pools that he's deploying right now to be prepared for this? We don't plan for this to be something that would happen as part of the upgrade. So, if you build a pool, its label will be the current label. We might be able to get some of what Matt's talking about of, we stick the header NV list maybe as part of the boot environment area. Or no, we overwrite that though. Anyway, we'll find a good place to put this NV list that will make the label more extensible. And it will mean that in the space we have for an old-fashioned label, we would be able to have more flexibility on how we use that space, even if that is just, our VDEV config isn't using all 112 of these kilobytes, we can use some more of that for the Uberblock ring or something like that in order to give some of these advantages to pools that were created with the old layout instead of the new one. But currently we don't have anything where we could say, align the first DVA with the 1 gigabyte boundary instead of the 4 megabyte boundary in order to leave us room to grow the labels in the future. Paul?
Yeah, so, I mean, obviously I think there's a lot of really interesting stuff here to talk about, and happy to talk about a bunch of it offline later, but specifically for the sector size stuff. The thing that I was thinking, and I think this ties into the point you were making, is that the choice of 16 megabytes as sort of like the worst case scenario, do we have like specific data that suggests that is an actual sector size that will be targeted, or that it is the biggest sector size that will be targeted, or does it make more sense to do something more dynamic, where we can say like, oh yeah, the sector size for this device, when we create the pool, we're like, okay, the biggest sector size we're going to have for this pool is 32 kilobytes, and so we size all of those things based on that size rather than pegging it to some biggest size that we're ever going to encounter in the future.
Right, so the biggest size I picked there was just from the max record size. If the sector size is bigger than that and we can't have a record as big as the sector, then we're always going to be wasting space.
Right.
But yeah, kind of to Mav's idea, we could, by using a header, we can make it a lot more dynamic and not have to give as much. I think we might still benefit from reserving that first whole gigabyte, but sizing everything based on a more realistic max A shift for the time probably does have a lot of advantages.
No, aside of Uberblock, everything else will likely write in one go, in one operation. So we could just pack them together to write them together to not bother with this here, this there, this there.
Yeah, it might even, like you said, probably better performance to write them all packed than to, write 32 kilobytes here and then seek and then write another 4 kilobytes there and seek and write another 4 kilobytes here, and so on.
And one more issue, not directly related, but we hit with block ID with pull detection. That if you create ZFS on top of ext4, on top of VMFS, on top of Linux RAID, and some other cases, block ID detects those first, even so ZFS was the last. With such a big amount of holes that we never overwrite, we may not be able to import the pool we legally created just before that.
Yeah, so we might also take to kind of prophylactically zeroing out the label before during gpool create so that we get rid of whatever ext4 signature might be in that first 8 kilobytes of padding that we don't normally write it to the label. And make sure that block ID isn't going to pick up a bunch of stuff that is from an old, like we've seen this problem on FreeBSD where if somebody had used the motherboard RAID and that signature was there, the GRAID driver would see it and then it wouldn't be, ZFS would say that disk's in use, I can't use that one. We don't, I looked at something with like gpart of like, wiping the first and last 1 megabyte of the drive or something, but maybe zpool, when we're creating it, we should, try a little harder to make sure there's no other cruft left on the device.
No, yeah, it's maybe a bit of a hack, but instead of like, if we leave first 32 megs of disk campaign, we can collect all the problems we could. It would be worst case. Yeah. While writing from the beginning, it would give us slightly higher chance of actually
of clobbering all the leftover gunk.
Yeah.
Paul, go ahead.
The thing I was thinking about when you were talking about the meta slabs for the like ultra large VDEVs. I did a bunch of work on Metaslab performance not that long ago, so that definitely I was thinking about a bunch of things there. But one idea that occurred to me that's relatively straightforward that wouldn't require a lot of other changes is that like there's no particular reason that one VDEV has to contain exactly one Metaslab group. You could have sort of like internally sharded that VDEV into 10 Metaslab groups that would, have a smaller total size, and then you could they would be able to be treated by the rotor just like having multiple separate VDEVs would. Mm-hmm. And that would also mean that metadata would get stored at different offsets in these giant disks, which might help improve reliability in case they have an underlying storage failure or something like that. And also would bring the Metaslab sizes down so that you wouldn't have
massive
and the counts down, so you wouldn't have quite as catastrophically bad of a time when searching for space.
Yeah, I think that could be very useful. And Don has been toying with the prototype idea of being able to grow the size of the Metaslab to reduce the count on existing pools by just, take these 4 small Metaslabs and combine them into one and kind of work through the list and rewrite them all.
Nice.
But yeah, I think possibly having multiple groups could also be a good way to scale on these supermassive disks.
Yeah.
Of many Metaslabs that we have to
Patrick,
update all of them.
Oh, okay.
So a problem with all the many Metaslabs that we may have to update a lot of them. Mm-hmm. We have already a shared log, but we need to flush it sometime. I'm not sure that the reducing number of Metaslabs save us dramatically, or reducing number may help, but I'm not sure how sharding would help unless we start preferring to fill those completely until we even start thinking about others. Mm-hmm. Right now, we prefer the best Metaslab we could, but maybe we could remember what we were doing last and continue. While we are running, we should do that. We continue running the same Metaslab until it got a threshold worse than the next before switching. But maybe we could extend it for longer periods of time.
Yeah, and I think, Don, you also found that once we hit half full, we move on kind of too soon sometimes?
Well, when you're allocating big blocks, it just gives up and goes somewhere else. And then your entire pool is all half full.
Yeah, so there's probably some more behavior changes in there. Go ahead, George.
Yeah, and I think the other point here too is that as you start doing big blocks, you may want to segment big blocks to certain metaslabs while your metadata, which still remains relatively small, is being written to different metaslabs so that you don't end up creating more fragmentation as you, if your allocations are mostly 16 meg, and then you're throwing a 4K block in the middle. When that gets freed up, that space is really only going to be usable by other metadata. So you're going to have to figure out like how you kind of balance that, and maybe with these large drives, it's obviously a little bit easier.
I think we could take a look on allocator code, because right now allocator with by default it tries to split allocations by power of 2. I'm not sure how much reasonable is that, since we have compression for a long time and now sizes are pretty random. I was thinking we could maybe just within MetaSlab, instead of having 32 or 64 pointers, we could have, okay, if this is part for smaller blocks, write sequentially, that part try to dedicate for bigger one and write sequentially. As we can write sequentially, okay, we'll wrap around to do something else, but I don't think logic of power of 2 actually makes sense. So maybe we could, like with embedded slog, differentiate by usage. I'm not sure was it separation of data versus metadata makes sense or something else. But if we could predict keep time of the data, how long they will be on a disk, maybe that we could group on.
Yeah, I wonder if there's advantage of if most of our metadata is packed into one metaslab, if that means we can aggregate the reads better sometimes. When we're reading a super large file that's going to have a whole lot of tiny bits of metadata, if they happen to have been all allocated from one metaslab, maybe they're a lot closer together when we need to read them. But then again, over time, maybe they're not.
No, we would need to write files completely sequentially, or for most part sequentially, for the indirects appear into nearby blocks to actually matters. But I wonder, would it allow us to reduce overhead, maybe, write inflation? Because right now we are writing metadata, then we're updating space maps, writing, and it's then we deleting something and again updating the space maps, and it's not even updating in the same metaslab. We are writing one metaslab while dirting several others. To flush those, we update a few more, and it's total noise through all the pool. Yeah. If we could maybe localize that. Right now, metaslabs are space maps not stored in metaslabs themselves; they stored anywhere, and that creates weird effects I saw.
Yeah. Paul?
This is a slightly separate topic of discussion, so if other people have points on this, we can go to them first. But the another thing that I was thinking about when you were talking about, like, how do we know what kind of drives the user is using, like how do we like get that information so that we can like properly plan our queues and our like access patterns and all that kind of stuff. It feels like as storage there's so many more storage options now. It feels like one thing that we might want to do is have a, like in addition to the existing zpool create and zpool add interface where you like specify sort of your VDEV patterns in these like, in this very short format, it might be nice to have like interactive zpool add where you can like build the tree and like it'll show you what the disk layout looks like. This would also help with people who like accidentally do attach instead of add and things like that. Mm-hmm. And then we could also have a way to say like performance hints where this user could say like this disk is an NVMe, and so like we would know when we're doing our planning what things look like there, and like we could give the user the option to provide more data and hopefully use that to make better decisions.
Yeah, like we've also considered that for VDEV properties. Like, how do you specify VDEV properties at zpool create without making the zpool create command line atrocious? And so maybe interactive lets you do that and would let us ask people, hey, while you're here, do you want to configure how many checksum errors per 15 minutes will trigger replacing this with a spare? Or, if a disk is slow, do you want to auto-replace it or not? And that kind of configuration, in addition to, hey, can you tell us something about what kind of disk this is? Because that would let us suggest the right tuning for you, and kind of, to Mav's point of yesterday, lead to users not twiddling the kernel module parameters themselves as often as possible.
It's still fun for some of us. But
Stu, can we get Stu's mic?
what we talked about on Saturday was actually having a profile of, hey, here's a standard set for spinning disk, standard set for NVMEs, a standard set for, we actually tried 1 petabyte large LUNs, sucked. 500 was, through marginally excessive testing, was the high water mark for that. So figuring that out ahead of time as part of the testing plans and everything else, hey, here's the feedback from us dumb users to say, hey, here's how we need to tune to actually get the performance we're expecting out of really expensive hardware.
George?
With like the NVMe work that you were looking into, is it possible to discover like how many queues are the drives actually reporting that information back, and do we have kernel interfaces to actually get that?
Yeah, so they report it to the OS. Whether ZFS can easily get that or not is probably very platform dependent. But to some degree, yes, that you can actually find out from the device that, hey, I have 63 queues with the 64th one reserved for admin commands that have, you know, a queue depth of 64 or whatever.
If it's not abstracted away by
virtualization. Yeah, and then
that's where the tuning side of it comes back into it, of, hey, I know what's really happening at AWS, this is what I need, versus real hardware.
A tool that goes out and probes the drive a bit and says, here's what the performance I can get out of it doing.
But what it's giving you, you know, from that probe test, you know, an AWS or GCP or whatever saying, no, you're getting this drive and it looks like you're not getting the real stats underneath of it. However, it is a tunable, in my mind, to be able to go and fix that. Versus, hey, here's physical hardware, here's a abstraction layer. And
and we talked a bit about that earlier in the presentation about like, yeah, we could do some tiny benchmarks and try to make a good guess from that, but how do we make sure that the hypervisor doesn't happen to have cached the first couple of reads, and so we get this performance, but then later we get that. Or even consumer-grade NVMe devices have a limited amount of SLC, and so they'll write really fast up until they fall off a cliff, and then they'll write really slow. And how do we try to discover that other than, you know, oh, we're just going to throw a terabyte at this disk and see if it ever slows down, and things like that. But yeah, we can at least do something, even if it's not perfect, because it'll get us better than just assume everything's a hard drive and it's up to the user.
80% of the way there and the rest is tunable. Fantastic.
Right, yeah, so you want probe plus hints.
Right, yeah.
Can we get Steve's mic?
Could you talk a little bit about what you see as sort of the low-hanging fruit in terms of concurrency, adding more concurrency? You talked about the separate queues of async writes and the scrubs and everything is sort of serial today. What do you sort of think as low-hanging fruit versus like hard stuff to do in adding concurrency?
Yeah, I think possibly the low-hanging fruit is looking at, can we get dedicated threads just firing I/O at the disk, but at the same time, with the fact that each queue on an NVMe is per CPU, maybe that's not the best way to do it. And we actually want to do more like direct dispatch. So when an application is running on CPU N and does a write, we want to put it into that queue for the NVMe, and rather than going to sleep and letting some other thread tell us when we should wake up and continue processing that, we directly like sleep on it and get the answer back really quickly and return to the user while all the other CPUs are doing the same thing on other queues. But you know, if you're doing that, if you're doing direct dispatch, how do we make sure we're actually getting some queue depth as well? You know, if you only have 32 CPUs and you're using 32 NVMe queues, then if you're only going to have one command in each, you're probably not going to get all the performance either. So what the right trade-off is not completely clear yet, but you know, we've seen that there's probably a decent amount of low-hanging fruit in that area.
All right, well, thanks a lot.